So thank you very much. Today I would like to present a study that we have begun maybe 10 years ago. And it's about a basic research about the reason why the semicrystalline polymers exhibit such mechanical properties. And it's very important in the framework of the work we have performed with Sendai University, because the point for semicrystalline polymer is that we don't really know the origin of the good mechanical properties, and we have to go back to basic research concerning the local reason of the mechanical properties. And the problem is that there is no experiment that can allow to give this information. So we have to perform molecular dynamic simulations and to look at the topology, the very local topology of the chains for this polymers. So this is the work of our two PhD students, and this is essentially the work which I supervise with Julien Mortemas. Okay, so here this is the microstructure, general microstructure of semicrystalline polymer, which is in between amorphous and crystalline. We have lamellar, crystalline lamellar, and in between we have an amorphous phase, which is very complicated. And the mechanical properties of the polymer is given both by the mechanical properties of the crystalline lamella, which gives essentially the stiffness and also the yield properties. But the long-term properties are given by essentially the amorphous phase. And here is the complexity of this kind of material, because in this amorphous phase, the question is its ability to transfer the stress between the different lamella. And there are many kinds of chains. There are chains that are linked to crystallite, which are called tie chains. There are loops that come from a crystallite and come back in the same crystallite. There are some cilia or pending chain that goes from a crystalline, and the end chain is in the middle of the amorphous phase. And all these kind of chains should play a role on the mechanical properties, and we have to perform simulations to be able to understand that. So we have built a coarse-grained molecular dynamic model. Coarse-grained is because each bead represents, let's say, 5 to 10 monomers. The advantage of such a technique is to be able to reduce the time of simulation. So we use Lennard-Jones potential, in which we have chosen a specific distance, so that by choosing this parameter, the chain is able to align easily. And when the chain is able to align easily, it means that the crystallite are easy to appear. And in that case, we have a lot of crystallinity, which is exactly what we want in some lattice that can be body-centered orthorhombic or hexagonal primitive. In fact, it is essentially a body-centered orthorhombic that we find in our system. Okay, so we get this kind of microstructure. You have here the enthalpy, which is a variation of the enthalpy, which decreases a lot when we crystallize this. Where we speak, maximum of crystallization is here. And then we get from a high temperature, here the units are Lennard-Jones units. And from high temperature to low temperature, we see the crystallinity, which is created and which is increasing along the decrease of the temperature. at the end, we can get on this system, which is a very simple system of 500 chains only with 100 bits per chain. We get some typical crystallinity of 60%, which is very consistent with what we can see in the reality. The only problem is that this microstructure is a bit random, and then we have to improve this point. But I will discuss that just after. So here we performed a lot of tests with this same technique. We use here, it's an example with a different system, a lot of different systems, which are with a different chain length. Here, it's a mixture between long chain and short chain, and we have just seen if the crystallinity was comparable to a classical system, but it's just to show here how it works. We have the enthalpy and the isotherm time. I mean the time spent at a given temperature to favor the crystallinity. For example, here we are at high temperature, and we go from the beginning of the crystallization with some nuclei to the end of crystallization, okay, after waiting, in fact, a long time. Again, this time is not directly comparable to the reality, but this time allows to fulfill finally the system of crystallites. It's the same for a lower isothermal temperature. Okay, the only difference is the number of crystallites and also the crystallinity. So this system are satisfactory because they are realistic compared to what we know about the crystallization in the real systems. Okay, also we have measured on this system different properties of the amorphous phase. The number of cilia, the number of loops, the number of time molecules. So I won't describe it in detail here. I will do it just after. But we have checked that this kind of molecules behave, I mean, realistically, because we don't have any clear information in the reality because it's just a point. But we have just looked at the fact that these evolutions are realistic. In particular, the number of cilia decreases with the increase of crystallinity, which is quite logical because the chain goes in more and more into the crystallite. Okay, so here we have finally, let's say, 5 systems obtained at several temperatures. And we have here lower temperature with low crystallinity, a lot of crystallite and little crystallite, and the lamellar system that we expected, which is what we see in the reality for the higher temperature. So these systems are satisfactory because we find what we see in the reality. So on this kind of system, we can be confident with the fact that we can use that to try to understand the origin, the deep origin of the mechanical properties of the semicrystalline polymer. And we have also different crystallities in relation with the isothermal temperature. Okay, so we have tested this system in terms of mechanical properties. So it's just a tensile test that is possible to realize with these simulations. And the tensile test gives these strain results, in fact. This is the stress and the strain. And we see for the different system I just showed before, which has been obtained at a different temperature, we see that all the system seems to behave the same, and it's very noisy also. And in fact, the reason for that, in fact, there are two main reasons that shows that our system has a problem. So the first problem is that, in fact, the crystallites are very weak And it is very easy for the chain to be pulled out from the crystal, which is not realistic for the real system. But our model is too simple, and it's impossible to prevent the chain from being pulled out from a crystal. So it means that the crystallites are very weak. Also, the system is anisotropic, and when we stretch it, it is difficult to compare the different systems because the different crystallites didn't grow in the same direction, and it is too little to be averaged. So it is difficult to compare. Okay, so for the crystallite, we try to improve the strength of the crystallite, but finally it was very difficult. And in the first step, we didn't improve that. We tried first to improve the problem of anisotropy and just to try to compare different systems. So we built 3 different systems of 200 bits, 300 bits, and 500 bits. There is the same number of atoms at the end, of bits at the end. But we want to build a system with lamella in a specific direction. So we use this idea, which consists in putting some nuclei, which is only 5 chains, which is perfectly aligned with the Z direction. 5 groups of 5 chains, which are perfectly aligned in the Z direction. And then we let the system crystallizes. Okay. So we let the system crystallizing with this nuclei, and after we cut the chain in the middle so that it doesn't change strongly the topology of the system. And of course, the crystallinity is increasing. And again, we can measure the number of loops, cilia, and time molecules, which here seems to be much more constant because the crystallinity grows very, very quick. And then we obtain at the end a beautiful lamellar system, which is perfectly oriented in the Z direction. And now we can begin to compare different ideas or different systems. So the first thing we have done is to perform this kind of modeling with the 3 systems I have showed before, with 200 beads, 300 beads, and 500 beads per chain. So for this system, we have an isothermal crystallization at a given temperature, and we see the crystallization with a decrease of energy and the volume and so on. So it works as expected. And during the increase of the crystallinity, we get again, and this is the interest of this kind of simulation, the complete statistics of any change in the amorphous phase, which is what is invisible in the real life. So we can have everything. For example, here, the decrease as before of cilias, the increase of time molecules, the increase of loops. So with this statistics, we want to analyze deeply all what is happening to the amorphous phase during crystallization and after during a tensile test, and try to understand the origin of the mechanical properties from the topology of the amorphous phase. So first of all, we use an indicator of the equilibrium, I would say, of the chain, which is the MSID, which is the mean square internal distance, which is the distance between 2 atoms inside the chain for any number of beads. And then normally the equilibrium is close to this black curve, which is an increase, and then a constant. It's an end-to-end distance. And when we crystallize this, the system, we see this big peak appearing, but it's just because the chains are aligning in the crystallite, and then the distance, the internal distance, is increasing. So this is not the most important indicator, because it mixes both what is happening in the amorphous phase and what is happening in the crystallite. So we have performed same kind of analysis, but for each kind of chain in the amorphous phase, which is the most important goal for this study. I mean, the aim is to understand what is happening to each kind of chain when which crystallizes the material, with the idea to be able after to understand better the origin of the mechanical properties. So here we have the MSID, the internal distance of the cilia, the pending chain, the amorphous phase, but depending on the size of the cilia, because the pending chain can have a size in the amorphous phase of 0 to 40, or at the maximum 200, because the size of the chain here is 200. There is a very few number of big chains, as we can see here at the end, but I will discuss that after, and much more here. And this is quite difficult to read, but the idea is just to compare these different curves to know if they are just a straight line or something different. And as we can see for the cilia, at the beginning and at the end of crystallization, it seems to be more or less the same and more or less horizontal, meaning that the cilia seems to be at the equilibrium, which is quite logical because they are free. The end chain is free, so the chain can relax, and then they should be close to the equilibrium. Also here we have the statistic in terms of number of cilia, little cilia, and very big ones, and we see that there is a lot of little which get constant, and for the longer ones, there are less and less, they decrease, and for the very long, there is a very few number of cilia. It means that most of the cilia are very short, in fact, which is very important for the mechanical properties, because if the pending chains are very short, it's difficult to transfer the stress. We have the localization of these different cilia, and as we can see, when the crystallinity is finished at about 2.0, this is the time, they are located, of course, in between the lamella. And okay, well, I won't discuss that. It's quite logical. And just to see that we can have many information about this system. We perform the same from the loop. We have, I will begin by the number, which is quite comparable to cilia. There are a lot of very short loop, a little, from 40 to 80 is quite significant too, and then it decreases for the very long loop after the end of crystallization. And for the internal structure, the MSID, the internal distance, we see it's different. It seems to decrease with crystallization. It's not a straight line. It's not a plateau. So it means that the loop are quite in a situation which is not the equilibrium. It's difficult to know what kind of role it can play on the mechanical properties, but it's clear that we can see that it's not at the equilibrium. So it's maybe an important information that we will have to correlate to mechanical properties, which is not obvious, of course. But okay, it means that it's like the ensuring of the loop are too close each other to what they should have been if there was if the crystallite didn't exist. So it's not an non-equilibrium situation for this kind of chains. Okay, so again, there are the localization, which is of course in between the lamella. And here we can see that, for example, here the crystallization is not over, so the loops are everywhere in between the different nuclei. And then the perfection of the of the lamella increases until the end, where the loop are of course in the lamella, the amorphous phase, which is a lamella in between the crystalline lamella. Okay, and we have performed the same, of course, for time molecules. And again, we see here it's quite difficult to interpret here because there are some strong fluctuations. So it's difficult to say. Maybe there are some time molecules which are too much taut, and other time molecules which are maybe very folded. So the average is in the middle. It's not far in average from the equilibrium, but maybe it's the distribution is very high. So it's quite difficult to interpret. And okay, we have also much more short time molecules at the end of crystallization than very long chains, very long time molecule, which is normal, of course, because the crystallinity is high. So most of the beads are included in the crystallite. So of course, there is the probability to find a very long time molecule is very low. Okay, and here the distribution again of this molecule in between, of course, in the amorphous phase, so in between the lamella phase. Okay, so now I will finish by the determination of one of most important parameters for the amorphous phase, which is again completely invisible in the reality, which is the entanglement, the ability of the chain to entangle together, which prevent the mobility and then play a significant role of stress transmission and then on the mechanical properties. And so here we have a PPA primitive path algorithm, which the aim of this algorithm is try to see artificially the entanglement. So for example, here in black, we have a given chain. And what we do is we lock the end chain and then we stretch the system just to get at the end some straight line. Okay. And here in blue, you have this primitive path, which show that at the end of this stretching, you have some turns, and each turn corresponds to an entanglement. For a short chain, is the same. Okay, and at the end, the primitive path for this chain is very easy. There is only one turn, so let's say one entanglement. Okay, I can discuss this detail after if you wish. Here, for example, for lamellar structure, which is not the same system, but anyway, this is the same procedure. In between two lamella, you have the system at the beginning, and after this primitive path algorithm, we see stretching in this part, and then we see some term which correspond to entanglements. Okay, so we use this algorithm with our system, and then we found, in fact, a decrease of the density of Z1 here, which are the entanglements, with the crystallization. Okay, and this is for the whole system. So it means that the crystallite are also destroyed by this algorithm, and then the localization of this entanglement are nearly everywhere. So in fact, we perform again the same procedure, but only in the amorphous phase. And then we see that there is here a little peak, which gives the probability to find a chain with only 3 or 4 entanglement. And then there is a much higher probability to find chain without any entanglement, which is quite logical to what we said before, because we have a lot of very little chain in the amorphous phase which can disentangle. And so the density of entanglement in the amorphous phase is decreasing with the crystallization. Okay, and now we have this entanglement which are localized in the amorphous phase, which is quite logical. So now the mechanical properties, which is again difficult to interpret, but in the direction here in green and black, we have the tensile test parallel with the lamella, And we have very weak properties due to the fact that the lamella are very, very weak, as I said before. So we didn't change that at the moment. And in the Z direction, the mechanical properties are much higher because the amorphous phase play a significant role. So this is the red curve we have to interpret. Finally, it's not so easy, but okay, this is our result. And here the units, again, our Lennard-Jones units, it's not easy to compare to the reality, but it's, okay, I can discuss that after. It's not, it's quite consistent, in fact. Okay, so in fact, we did that for a different system. Okay, I will skip that. And we did that for the other system, so 300 bits per second and 500 bits per second. We have exactly the same information. I have all the slides here. I will not show you everything because it's in fact qualitatively very close. And I just have the slides just in case of any questions, but it's the same analysis for the different systems. So I will skip all the same analysis, in fact, for these systems, for this first system of 300 bits, and it's qualitatively exactly the same thing. But there are some differences that I will discuss after in terms of mechanical properties. So again, we have all the topology. And again, the same for 500 bits per second. And again, I have all the data if you wish to have any question about that. And this is the interest, by the way, of this simulation, that we get finally the position of all the atoms, and we get a huge amount of data each time for each system. And okay, qualitatively, it's the same. But now what is very interesting is to compare these three systems together. So I will not compare everything, because again, it's extremely, it's a huge amount of data. But I will compare only two things, which is the density of entanglement in the amorphous phase for the three systems, 200 bits, 300 bits, and 500 bits, versus the time of crystallization. And you see that this density is decreasing, which is quite an important result and not so easy to understand, because we could have think that the density of entanglement should increase with crystallization if we push the entanglement in the amorphous phase and if we don't destroy it. But the decrease is just the reason we have explained before, is because we have a lot of very little chain in the amorphous phase, so they relax and they disentangle, in fact. So it's an important result because it's likely that when we decrease the density of entanglement, we weaken the amorphous phase. So it's, in this case, it seems that this is also a very important cause for the weak mechanical properties we have seen. The second thing we show here is that for 500 bits, the decrease is much lower, which is normal and expected, because the viscosity is higher and the possibility for the long chain to entangle is much higher. Okay, so if we look at the comparison of the mechanical properties, not so easy again to compare, but okay, I will just forget the two y and x direction, which are very weak due to the crystallite. But for the red curve, what we see is when we increase the number of bits, the slope is slightly increasing, which is consistent with what you said before. I mean, it's consistent with the fact that the density of entanglement is increasing. But okay, the yield is difficult to analyze, even if it's probably due to the crystallinity, which is not the same and which is much higher for this system. But okay, we are on the way to connect the local topology in the amorphous phase to the mechanical properties. Okay, so to sum up, we have built, it's a very long time that we work on that, a model that represents realistically the real systems. We perform a tensile test. As I said, we have some problem of pull out of the crystal, and then the crystal is too weak. But anyway, we can use this system to test in the Z direction on oriented system. We can test finally the amorphous phase and try to understand the mechanical properties in relation with the topology of the chain. And of course, we have the mechanical properties of this system strongly depends on the topology of chain, Schur entanglement, loop entanglement, interface, time molecules. And we have to connect, we are trying to do that, to connect this topology of the chain with the observed mechanical properties, just to understand the origin of the semicrystalline polymer, which is in fact not really understood at that point in the literature. And also, we would have to improve the mechanical response of the semicrystalline polymer. I mean, we would need to do that to change the mechanical properties of the crystalline, which is at the moment not so easy. Okay, and thank you very much.